Fantastic, Amir. Thanks a lot. And I will have to buy a bit of time because actually, what nobody knows is we got another speaker today. I invited some of my colleagues, but he is currently rushing to the office, so he will be a little bit late. Anyways, I'm going to start, and I stretched my part as far as I can to let Jeff join the call later on. All right. So, well, thanks,
I'm
Amir.
here.
Oh, fantastic. Great, Jeff. Okay. Thanks again, Amir. Thanks for inviting us to talk in this working group. It's really exciting opportunity, I think. And so to everyone, hello, good morning, good afternoon, good evening, wherever your time might be right now. For me, it's an evening. Welcome to this talk, which I envision to be a summary of how we at AWS think about quantum computing in a cloud model, obviously. Uh, for both, for accessing quantum resources, but also for integrations with classical compute. And hopefully we present this in a way which is most useful for this diverse audience here. I gotta say, I did have the chance to attend several of these framework presentations in our openQSE meetings, and each and every one has been eye-opening and made me pretty sure that we all here share the same vision, whether we are hardware vendors, whether we represent centers or ISVs or cloud providers, which is clearly to make quantum computing a foundational technology that will complement the portfolio of accelerated computing we currently have, right? And that we eventually want to use it in a similar way as we already use our other accelerators we got. Now, for AWS, as we are a rather large provider for compute in general, with currently more than 750 different compute instance types, think of compute configurations, available on Amazon EC2 for our customers to select based on their requirements, what they need for the various workloads. And as we are offering already a diverse portfolio of accelerated compute options, be it GPUs or FPGAs or purpose-built accelerators, including our own silicons, we obviously ask ourselves too how we can provide quantum acceleration integrated as seamless as possible in our offerings. Now, clearly we are not yet at the stage depicted here on that slide, right? This is a bit scientific, a bit science fiction like. We don't have QPUs next to, well, we have QPUs next to a couple of our accelerated instance families, but these can, scale out elastically and are virtualized in some form. So we are not there yet. For that talk here, we take back a couple of steps, and we want to share and hopefully trigger discussions in what we have built so far and what our customers are already using day to day since a couple of years. Now, as I said, we a couple of times, and by now you already know it, you heard Jeff. So who are we and what will we talk about specifically? Well, I'm Sebastian. I'm a specialist solutions architect for quantum computing in our worldwide advanced computing team. And I'm really delighted that I'm joined today by Jeff, our senior software development engineer on the Bracket team. I will kick this off with a general introduction to Bracket and focus a little bit what features we offer to our users, and then hand over to Jeff a couple of times, who will give us some insights into Bracket internals. A couple of weeks back, actually, Amir asked me if we could add something like that to the presentation. I wasn't sure back then, but I'm really happy that Jeff is around to lead that part of the conversations. And then in the last part, I actually want to come back to the user perspective, and we will talk about how we think about integrations of quantum and classical compute resources. And this is then hopefully not too cloud-centric or not too AWS specific, and I would love to have animated conversations about such topics and get tons of feedback from you guys. Okay, so let's begin in the beginning. Amazon Bracket, this is really just the name of our quantum computing service in the cloud. It's generally available now since 2020, and everyone with an AWS account can just use it. And what Bracket does predominantly, it gives you access to quantum hardware, actually from various hardware vendors we are partnering with. And you can access these QPUs by default in on-demand access mode. So that means you only use a quantum computer when you need it, right? And you only or get charged for it when you use it, requiring little ahead planning, zero commitment in the best tradition of cloud computing.
Oh.
Alternatively, what we got is you can reserve time on a QPU. You get dedicated access in that case, and the device is all yours for a certain period of time, which you have reserved upfront in that case. So that to the hardware access, now Bracket is not just a portal to these different QPUs, I would say. The service itself actually provides a what we call a unified developer experience to all these different hardware modalities. It means it takes care of queuing or scheduling for program executions. It by default compiles the circuits from the logical representation users can specify down to what can be actually executed on the device. And then at the same time, it also allows expert users, I would say, who need more control over what is executed to program in a device native way. Users can take care of compilation on the client side. They got access to the calibration data to take that into account if they want. And for some QPUs, you also get pulse level access. Now, already a brief outlook to the last part of the talk. When it comes about quantum classical integrations, the service itself already provides an execution environment for hybrid programs. In that case, it takes care of both the underlying quantum and classical resources. And another aspect, which is, I think, often overlooked, well, from the perspective of an AWS user, Bracket is really just another service. We made a very deliberate decision to not make this a standalone tool, but a first-class citizen of the AWS cloud. And as such, it can be seamlessly integrated with all the other services and also built, and I mean, this is where the presentation today will end, also built for purpose hybrid quantum classical environments. Now, I would say let's delve into the individual bullet points here a little bit deeper. And the first is quantum hardware. Now, since the service has been launched, we have integrated, I think, 24 different quantum computers from in total 8 hardware vendors. You see over the years, we have onboarded devices from new hardware partners, as well as we have upgraded to newer generations from existing partners. And right now, we offer 8 different QPUs from 5 vendors, including ion traps from IonQ, and our latest addition last autumn, AQT, superconducting QPUs from Rigetti and IQM, and then also neutral atom QPU from Quera, Aquila, their analog processor, compared to the gate-based or digital devices mentioned before. Well, we are committed to continue this work, right? We maintain close relationships with the existing vendors, and we're going to adopt new technologies as they become available. Along that way, we obviously learned a lot, and I want to now pause here and hand it over to Jeff, who will talk a little bit about device integration in the Bracket service.
Thank you, Sebastian. So as you can see, we have tried to unify the device integration as much as possible because we've had to partner with several different companies who have, very early on, people had very different ideas of how to connect. We had combinations of web APIs, gRPC, direct socket attached messaging systems, very bespoke systems. And so gradually we were able to build up a abstract hardware API to focus on how do you actually interact with a given device. And so to that end, we sort of evolved into Happy, which was a hardware API that allowed us to wrap all of the commonalities of how you would want to interact. Obviously, things like creating a task on the device, getting that task status, canceling it, adjusting parameters. And, one of these things is frequently hardware providers will also have the some nativization step. So we would also include this ability to invoke additional APIs around compilation, translation, binary encoding, that sort of thing. We also found that as we evolved, like we needed better security models. Amazon takes customer security very seriously. We are pursuing a lot of SOC compliance and ISO, I think it's 27,000 security compliance with several of our partners, and in order to try and make sure that we are protecting our customers' data all along the way. But also that means we've had to integrate with several different security standards, as well as manage devices and interact with the current status of the device, because without having a direct API for that, we were we would be unable to directly report things. We just have to see if tasks were completing or not. We were able to manage to get this framework built so that we could integrate with anything from REST, gRPC, custom Python libraries like PyQuil or Qiskit. And we've even managed to attach some ABIs into our Python stack through PyBind. Next slide, please. So users have several different possibilities for interacting. Predominantly, we have a metaphor of a quantum task, which is essentially a circuit with execution parameters on top of it. How many shots do you want to run? Do you want certain observables? That sort of thing. We also have hybrid jobs, which allow running a custom headless container in the cloud durably, and directly accessing the Bracket service, but also providing additional compute resources, large GPU-enabled compute systems, high memory systems, that sort of thing, through a partnership with the Amazon SageMaker service. We support multiple SDKs out of the box from AWS, the classic Python Bodo library. We have Java, C++, Rust, auto-generated API library interfaces, but we've also gone to the extent of creating our own Bracket SDK, which encompasses a lot more features around creating circuits, managing circuits, building a plugin architecture so that we can integrate with other circuit definitions formats like Penny Lane, Qiskit, and CUDA-Q. In the past, when we worked with D-Wave, we had a Ocean plugin. So we've tried to create an extensible ecosystem where we can collaborate with lots of different providers and partners to make sure that we're bringing quantum computing to everybody. Next slide. As I said, we start with a logical quantum program. We call it a task. You can define it. This is showing using the Bracket SDK, being able to create a simple bell pair circuit and just run it for 100 shots, and you can query the task queue, get the results. And so we have two dedicated REST APIs. We have a create quantum task for submitting these, where the service will pick that up and pass it to the QPU, and the get quantum task for checking on status until it's complete. One of the unique things about Bracket is get doesn't actually return results. We save those off to an S3 bucket, largely because we understand that a lot of the quantum workloads are going to get very large. Downloading those off the web is going to be a problem, but also because it gives our customers a persistence layer so that they can get back to their work if they figure out 6 months down the line that, oh, the thing that I thought I was looking for was actually this, and they don't have to rerun all of the workloads. Next. So some of the quantum devices we've worked with, such as Garnet and Rigetti's Anka, actually support pulse level control as well. So we've brought the ability to do that all the way out to the Bracket SDK so that you can actually define custom gates. You can use low-level verbatim circuits, meaning native gate sets that are actually implemented by the QPU's internal instruction set architecture. We also try and provide comprehensive information about the physical structure of the QPUs. So like we're looking here at a IQM Garnet lattice of how all of the couplers are actually connected between the qubits, and a table of the calibrations between all of those qubits. The verbatim mode does allow us to execute circuits directly in the exact order specified, but also, extend it beyond that. So you can have some very fine-grained control of the programs. Next. We've also extended up the stack a little bit to include batching. This essentially allows a customer to submit one or more circuits in a single API create call, and provide multiple parameters for each of those circuits, depending on what configuration of slicing and dicing you want. And then we will actually execute all of those as a block, so that we don't see as much calibration drift as you might if you were executing multiple circuits independently in the queue. You don't have to create a hybrid job. You don't have to reserve anything. You just sort of get these performance benefits. And next slide. So sort of looking at the overall flow of Bracket, how we manage all of this is, if you're starting with a hybrid job, you will actually supply either the identifier of one of our pre-built notebooks, or you can bring your own container with whatever packages you want in it, NumPy, SciPy, specific versions, that sort of thing. And we will spin that up and run that headless in the cloud for you. Either way, customers can directly access the create quantum task interface, so the job container can invoke this, or the customer can invoke it directly. We automatically validate every circuit as they come in to make sure that it meets at least the basic circuit parameters. So you aren't trying to run 1,000 qubits on an 11 qubit device or something. Once we've gotten through creation, we will actually take a look at the program, or the task specification, to figure out if there's a lot of batches, multiple circuits. We'll compile all of those down internally, and then do parameter binding after compilation. So we're actually doing parametric compilation on the circuits. This is a little bit of a there's a performance trade-off here. By having regular circuits, you're executing the same program every time with slightly different values, which in general will lead to a more consistent execution. But there might be certain cases where all of your parameters are 0 or pi, and we could optimize out a lot of gates that we didn't know at runtime, and instead you'll execute them in these low configurations, which might lead to additional noise. But at the very least, it's a trade-off the customer can make. They can submit it either way. We will execute a circuit that is already bound with parameters directly. Once we've finished binding the parameters, we'll dispatch it to the QPU, monitor, make sure that it finishes, and then we'll do post-processing, including expectation values, variance, amplitude. I don't use a lot of these myself, but we have these post-processing steps, and we will return the results for every individual execution of a circuit to your S3 bucket, and then we'll also include at the very end a sort of wrap up manifest of what was actually executed in the batch results, all of which gets uploaded to S3. And Sebastian?
Thank you, Jeff. I do not see the chat while I'm presenting, and so I just assume that we're gonna do questions or Q&A afterwards. That probably makes a better recording on your right. If not, and if anyone has an urgent question, please just open your mic and speak up. Okay, so thanks again, Jeff. We're coming now to the last part of the presentation, and this is about integration of quantum and classical resources, right? So now that we have learned about core features, core capabilities of the Bracket service, what we offer for task level execution, and also some of the internals, I want to transition this conversation over to how we think about offering users choice of integrating quantum and classical resources together, or integrating Bracket task APIs into their classical compute. And this is now really the part where I would be keen on feedback later on and open discussions. In my opinion, this is a pretty wide topic. This is pretty ambiguous, and it's not necessarily easy to pinpoint what users will need in the intermediate or long run, and which capabilities should be exposed, right? So it's clear that to me that we're gonna have to iterate. I mean, we as a community, and we should be careful not to oversimplify or narrow things too much. In my opinion, this is not a one size fits all thing. So therefore, I would like to address this as wide as possible in several dimensions. So the first dimension I want to look at is what do I need classical compute for, and how much? Clearly, the first thing that always comes to mind when we talk about integrations is are these iterative hybrid workloads like VQE. If I may make a side remark, I mean, to me, it's interesting that such VQE-like workflows still seem to be the default use case when we talk about quantum and classical integrations, even at the infrastructure level. It's not for me to judge, but I think it's worth to look at different patterns. So for that purpose, I want to give later on an example for a workflow requiring classical compute, by the way, at HPC scale for post-processing, loosely coupled, which may result in different requirements to such hybrid systems. And then on the other hand, what I find interesting is we may want to look into pre-processing for more complex compilation tasks. I don't know if that falls into that same domain. The second dimension I want to cover, I personally find very interesting, is where is classical compute hosted? Now, this is kind of indicated by this data center icon here next to Amazon EC2. I think we should discuss more the capabilities as well as the limitations, clearly, of, for example, on-prem stacks and classical resources extended with remote QPUs and cloud services like Bracket. I know it's a big surprise I say this, but also I find it's a bit underrepresented sometimes in the community. Although we already see many of such solutions in different forms. I mean, some of the hardware providers have their own cloud access models and so on and so forth. I will probably fail to cover that entire spectrum properly, but I will at least make an attempt to point to the different directions in which we have thought when we asked our users what they expect. So the first is hybrid jobs, and we've mentioned it a couple of times that Bracket offers this fully managed execution environment for hybrid quantum classical workloads. And to make it clear, this is, in my opinion, really built to make it easy for users to run such workloads in a consistent way. This is not only a cloud-only, but it's actually a service-only approach. But actually, I think it comes with some interesting capabilities I want to talk you through. So what's the user journey look like? Well, you see here a piece of code for a pretty simple Hello World hybrid program. The series actually variational. What we do here is a variational minimization of the expectation value for a single qubit rotation. Now, a user, let's assume, could run or could develop this program locally. For instance, develop against local circuit simulators, use classical compute of, I don't know, of their laptops. And then at some point in time, there may come up the need to scale this out to run a longer running experiment. So they might want to offload that, or they need access to QPUs and want to use QPUs in an efficient way, for example, or they need more classical compute. So within the picture of hybrid jobs, you can do this by simply adding this hybrid job decorator coming from the Bracket SDK. And that will turn this local function into a job, which is executed on Bracket when you invoke that function. This is the last line of the code here. So on the next slide, we see what the service does under the hood when we invoke this decorated function. So the SDK will will package and upload actually the function code. It will invoke the create API job, the create job API. And then what Bracket does, it stores and provisions, first of all, a job instance, one or more based on the user's selection. And the user can also specify basically the compute, can make a selection whether they need the GPU acceleration or not, or they have a CPU bound workload. So they have some flexibility on the choice of the job instance. Once the instance is prepared, provisioned by the service, then the service starts the job container. This again can be based on pre-built container images we provide, or users can provide their own Docker image to have full control over the runtime. And then once the container is started, we're going to execute the algorithm code. Within this job, when a user calls Bracket task APIs to run a circuit, let's say, then they will get in access to the priority queue. So every QPU actually has two queues, a standard queue and a priority queue. From within a hybrid job, you get access to priority queue, meaning that your task runs ahead of the tasks that are queued in the standard queue. I mean, both queues are FIFO, but the priority queue takes priority, obviously. Needless to say, you can also run on on-demand simulators provided through Bracket, or you can bring your own simulator if you can containerize it, if it's running within the job container. By the way, we also support distributing simulations across multiple nodes within the job context. So if you have a workload that requires a lot of many simulation tasks, for example, or you want to run, let's say, on GPU accelerated simulators, you can do that as well within the job context. And then, needless to say, once the job is completed and results are stored durably, like Jeff said early on S3, then we're going to tear down the instances so you don't have to worry about idling resources. So this is all great, but you do not have access to all the 750 plus instance types of EC2, right? So do you have a selection of service managed instance types, which may or may not fit for your purpose? So if you have special need for classical compute, hybrid jobs may or may not be a solution for you. And so on the next slide, I actually want to give an example where it was not the right choice. I want to spend some time, to introduce, this example for a real and rather big workload we supported in a collaboration with AstraZeneca and IonQ and NVIDIA last year. It was last spring or summer, I think. And I bring this up for, like I just said, for two reasons. First of all, hybrid jobs was not the appropriate tool for it, and second, it's a real life example with a hybrid algorithm requiring HPC scale classical compute. So in this four-party collab, we enabled a quantum accelerated Monte Carlo simulation of a chemical reaction. It was a nickel catalyzed Suzuki-Mayora reaction, which to my knowledge models critical transformation in the synthesis of small molecule drugs. And the team integrated openQ's FortoQPU with NVIDIA's Q2Q through Amazon Brackets to run a batch of 60,000 quantum circuits and then do a large-scale post-processing on an AWS-hosted Slurm cluster of more than 300 H200 GPUs. And if I'm not mistaken, that has been one of the largest of such experiments that were executed to that date and achieved more than 20 times improvement in end-to-end time to solution compared to previous implementation of this benchmark. Now, if you follow the QR link, for the curious ones, you get to an IonQ news blog. From there, you can click to a more technical blog, and you get also directed to the preprint on the archive. I don't want to focus too much on algorithmic details here. Just on a high level, what's the nature of that workload, or what is the workflow? So the algorithm that runs that simulation is an auxiliary field quantum Monte Carlo. It has two loosely coupled stages. The first is, in that case, performed on a quantum computer, and we're going to prepare some trial wave function of each of the of each of these three chemical systems here. And then we're going to use classical compute to perform imaginary time evolution to approximate the true ground state energy starting from the trial state. This part is completely parallelizable. And as I said, I mean, for the actual simulation, we use the GPU cluster on AWS and Slurm for workload management. But what we did afterwards, as an exercise, we thought about how a cloud architect with a lot of AWS expertise would have built that, right? And the result here was a cloud native compute pipeline orchestrating the quantum and classical processing steps through a serverless workflow engine and managing the HPC workload, not with a Slurm cluster stood up in advance, but rather with an alternative batch computing service and with containerization. Now, because I don't think there are too many AWS cloud architects in the audience, I'm gonna run over that rather quickly. The takeaway message here is, I mean, well, first of all, the purpose of this exercise was really to rethink how such experiments can be executed, and the takeaway was, well, the solution we came up with was not necessarily better or faster for running or executing the simulation, but it had big advantage in terms of portability, right? So the entire workflow with all the infrastructure needed is described in a YAML or JSON template and can be deployed through our, for example, IAC service CloudFormation. The application code is containerized with code and images being in the same repository as the infrastructure part. And that makes it really easy for distributed teams and such research collaborations to set up and develop and share their experiments. And this has been indeed a little bit of a bottleneck for our original experiment we did in this four-party collaboration. Okay, so that was kind of an excursus into AWS specifics. I actually want to come back now and talk a little bit more about traditional HPC environments. And I think, this is kind of also what now comes is a bit better matching with what others have presented in this meeting series before. So the topic is how can you access Bracket from traditional HPC environments to realize quantum accelerated nodes? Now, conceptually, what we have to do here is, well, first you have to allow your nodes to access Bracket task APIs, obviously, right? So, and principally, you can operate your very own software stack that is one, able to communicate with these APIs, and that two, ideally provide information about the Bracket QPUs to your workload management tool of choice. Now, such a system you can run in the cloud, or you can run on classical infrastructure in your center. I'd say in the latter case, you get kind of an extension to remote QPUs in addition to what you already have on site. And I think this is actually an interesting model. Again, we have seen such systems in previous presentations in this forum already. Now, for the case of brackets, I want to highlight a couple of our thoughts for resource scheduling because I know this is a topic of interest in this forum. The experiment we have run, kind of depicted here on the left, I'm skipping most of it in the interest of time, but just let me make one call out here. So for this experiment, we have used a service-managed Slurm cluster, where basically the Slurm controller is managed by one of our services called PCS. But conceptually, this makes no difference if you have a self-managed Slurm installation. But back to the resource scheduling approach. And I'm just realizing that I got the order probably in a suboptimal way. So let me start with option number 2, right? So option 2 here is pretty much what has been done by several folks in the community, I would say. It's just the AWS version of that. So if you use on-demand QPUs or on-demand QPU access, what you actually can do is you can leverage the get device API to get information about the device availability as well as the queue depth information. And then you can create your own Spank plugin to make aware Slurm of the QPU availability and also of the utilization. And you can then, upon these information, make a decision to configure your job for execution. So this is kind of the way we have seen previously in the community. There are a couple of solutions out there, and this is also something we experimented with. So perfectly fine. I just want to offer another option we were thinking about, and again, super curious to get feedback. So Bracket offers dedicated QPU access, meaning you can make a fixed reservation for a certain period of time of your QPU in advance, and you know exactly when start and end time of this reservation window is. And you can identify this reservation as well. Now, in principle, what you then can do is you can create a Slurm resource reservation, or what you could also, for example, do, at least, I mean, for example, if you have like a service, so again, for these managed Slurm services, like we have, you can also create Slurm partitions automatically based on informations in the reservation. You probably do not have necessarily this level of integration when you operate your Slurm environment elsewhere. So, but still, I mean, you always can go, for example, with a Slurm reservation, and then basically pair these time windows, and then you will be able to consume your classical compute capacity just in the same time frame where you have dedicated access to QPU. And in that case, it should really feel like you're owning your classical and quantum compute environments for the certain period of time you have both reservations on. Okay, so now that has been kind of the outlook of what we are currently experimenting when it comes to Slurm partitions within brackets. With that, I come already to the last slide, where I want to thank you again to Amir for giving us the opportunity to talk today. So what we have seen today, what I hope we gave you was an interesting overview of what different features and capabilities Amazon Braket as a cloud service for quantum computing actually offers. And then also some forward-looking experiments we have been running with integration of classical compute. All on the user side, meaning when the user has a hybrid application and they need control over classical and quantum compute resources. So thank you again, and I think we can open it up for questions. Not sure how we did timing-wise, 43 minutes. I hope that's okay.
Thanks, Sebastian. Thanks, Jeff. Okay, so Peter, go ahead.
Yeah, thanks very much for the nice talk. And you might have said this and I missed it, but so you talk about defining hybrid jobs via this decorator, but to some extent, like every quantum job is a hybrid job in a sense. There's a classical compute involved. So can you say more about what the difference is? And I think you might have mentioned there's a priority queue, but if that's the case, then why would anyone not use a hybrid job always and get through the priority queue?
Okay, so I think we have, let me iterate about a couple of concepts here. So I think the distinction we have to make here is Bracket offers a task level interface, and this is the idea of the task level interface is when you have just a quantum program, I mean a single task, a single circuit, sorry, or a set of circuits like Jeff mentioned. And that is executed. And clearly, like you said, I mean, there is classical compute involved in compilation and also in post-processing. But the user only wants to execute a quantum program. Now, hybrid jobs on top of that is created for the users that have a hybrid algorithm where they program their own classical and quantum subroutines. And that is the program that is the algorithm they want to execute. For that specific scenario, we have created hybrid jobs as probably one of the easiest ways to get started with these executions in the cloud. So hang on, nope, struggling with. So if we go in here, then because you mentioned the priority access, so we have again the single quantum program execution. So you just have one task, and it's either a single circuit or it's a set of circuits, and then you send this off for execution, and that goes into the standard queue. When you have such hybrid programs, and for the sake of the example, I'm just taking again an iterative variation or workload, then you have classical routines running between many subsequent quantum invocations. And in that case, what you as a user probably want, you don't want to queue together with people that submit individual quantum tasks, right? So you want to run this because you're running kind of multiple quantum task invocations in the context of an experiment. You want to get basically these executed as fast as possible, as close as possible in time. And so our approach to this was that we came up with the priority access. So these are kind of two different aspects here, what the user actually wants to do in terms of quantum or quantum classical execution, and then how the service handles queuing and scheduling. Did that answer your question?
Sure, thank you.
Thank you.
Cool. Sebastian, thank you for the great talk. Just a brief introduction. My name is Gwen Pereira-Mojo. I just joined INQ about a month and a week ago, so pretty new.
Congrats.
To the team. Thank you, and thanks for the shout out about the QC of QC. Sorry, it's a very long acronym. The Monte Carlo chemistry work. So yeah, that was the team that I'm on. Worked on that with you guys. I had a question. So I'll be leading the developer tools team. So we'll be working with Josh and Spencer and others on the SDKs and integration. So also working on the integration of Bracket. One question in light of this openQSE effort is, what is your team's like kind of strategy around open source? Like, is it like, I can think of it going two ways. One is basically you guys write tools. Like, for example, one thing I can think of is kind of the orchestration and queuing layers with HPC and classical compute, and then open source it. The other way I can see is that we as a community build those tools, and then you end up supporting that in Bracket. Like, what have you seen work really well in the past?
Excellent. So how we structure open source work. So when it comes to Bracket specifically, okay, I'm going the wrong direction again. No, oh my God. So Jeff told you about the individual, yeah. So the programming frameworks, for example, we support. So when it comes to user land in front of the Bracket APIs, then we are pretty big supporters of the open source community. So all of these, all of the tools you see there on the right are open source tools. So the Bracket Python SDK is open source. It is maintained by by our teams, but the code is open source, and we value, contributions in form of issues and pull requests, obviously. Also, the plugins and providers for example, for Pennylane and for Qiskit, these are also open source tools. Our engineers contribute, but there's also, room for and there's also, community contributions are highly welcome here. The only slight exception here is probably CUDA-Q, where they have kind of this native, so within CUDA-Q, this native support of specifying bracket backends as targets for their kernels. So there is not an extra provider package necessary here. So in that case, yes, so everything which is in front of the bracket APIs, we highly value community collaborations and open source. Now back to this hardware integration with classical resources. So here again, so everything which happens in the domain of the AWS users, we very much prefer open source. So in that case as well, if it's about making schedulers aware of bracket QPUs, we would certainly want to go more in open source than anything we want to build ourselves, and proprietary code does not make sense, in my opinion, at all in this context. But clearly then, because AWS is the cloud service provider, I think that everything is behind the service APIs is typically not open source code. Yeah.
Awesome. Thank you so much.
Thanks, Sebastian and Jeff. I have a couple of questions, well, a few questions. I'll kind of start from the top. You guys have this abstract API that handles multiple backends, right? You were mentioning it earlier on in the presentation. I like the name, by the way, Happy. It's nice. How, did you guys think about, because there are two other offerings out there, QRMI, QDMI, and from this kind of looks a little bit similar from the general output, or what you guys have listed there. Have you guys thought about aligning with those two efforts so we don't have so many different fragmentations of the APIs here?
Yes, we have actually. I've even actually visited Lucas and Robert Villa at TMU to talk to them about QDMI, and part of our experience was actually based on our integrations were at a point that QDMI was not quite ready for when we transitioned into using Happy. It was, and so it was mostly just a timing thing. We were trying to launch some new devices at the time, and we just needed something. We already had sort of evolved into this already. We are interested in consolidating. We do want to, migrate to a more uniform standard, but right now we're settling for convergent evolution.
Fair enough, makes sense. Thank you. Anybody else has other questions, or should I continue? For slide 14, if we go to slide 14 for a second. Right, so for the hybrid job, I guess maybe I didn't catch that. When you declare a hybrid job, the hybrid job has both QC and HPC allocations. Do you specify the number of nodes you need for HPC, sort of like you do in an HPC environment where you say S alloc, that number of nodes? Is that how you do it in the hybrid job?
In principle, yes. I mean, what happens under the hood is that there are, AWS service APIs which get called. But yes, I mean, there is. So what happens is the user. So in this create job API call, the user specifies first of all the so-called instance type, which is always a code word for what is the nature of classical compute, right? Do you need multi CPU cores? Do you need GPUs? What is the amount of RAM? I mean, all these specifications within AWS are encoded in these instance families and instance types. So the user specifies exactly that. And then they also specify the number of instances, right? So you say, I need 10 M5 2x larges. And then the service will spin up these instances, provision these instances, and make it available to you as the user. So that means you have that compute capacity.
Okay, makes sense. Related to that, if we jump to slide 20, and after this, I'll give up the floor for Thomas. Right, so you mentioned here on-demand and dedicated. So for the on-demand case, how can you guarantee things don't change under the hood, right? Like so you call get device API to figure out the queue depth, right? And then once you have that, you need to sort of orchestrate your classical side to make sure that it's ready to use the service, the quantum service in this case. But by the time your classical is available, things could have changed with the get device. So you have to keep repeating that somehow until you converge.
In principle, in that realization, yes. So I mean, just a very brief side remark: we are exploring alternatives here, and we are looking into things which we currently cannot talk about publicly. But I mean, we are aware of this shortcoming you just mentioned. But in principle, you're right. So in that picture, so on demand means really just there is a standard queue, and it's FIFO, and all the users, they kind of submit to that queue. Now, what you can do as a user by querying queue depth and general device informations, you can, I mean, in principle, you have control over when you think it's a good time to make available or to start your job and make your job available classical resources. And then from within the job execution, you then call bracket task APIs. And you're right? I mean, there is elasticity in this whole system, and there is no guarantee that while you start your job, nobody else submits 1,000 tasks. That's absolutely right. But you have control over that routine as a user. You can configure, for example, your Spank plugin, or write your Spank plugin, the logic in it in the way you want. If you really want to be sure right now that you have dedicated access for the QPU for the time you think you need it, then you would have to opt for a reservation.
And that's option number one, right?
And that's option number one, yes. And then again, I mean, here for option number one, I really just, I'm not saying you have to make a Slurm resource reservation, right? You can also handle classical compute resources in different way. But I mean, what you get from a QPU reservation is kind of a start timestamp plus the duration. So you know exactly the time window when only you are the one that uses the device.
Fair. It's just even with option number one, once you make that device reservation and say you're trying to use the offload of the diagram that you showed where you have the HPC is offsite and you're using the Amazon bracket service for that, you still have to somehow guarantee that your reservation on the Slurm end starts at the exact same time as your device, and or at least they overlap in the right way, right?
Exactly. So you as a user, basically configuring your workload manager, you have, again, a choice over how you exactly want to do that. I mean, device reservations in bracket now on the task API work in that way that if you call the bracket create task API with kind of a reservation identifier, then you can actually fill up, so ahead of time, right, before your reservation window starts, then you can already fill up the queue in a certain sense. And then as soon as your reservation starts, bracket starts immediately to process your tasks. So having said that, so you can in principle create like on your hybrid kind of layer, you can start your classical resources a bit ahead of time if you want that, to give your algorithm time to kind of pre-populate the queue if you want to do that, right? Or you can start right at the same time. It's really, I mean, that's totally up to the user to decide what's better for them, for their workload. If that makes sense.
Right. Yeah, no, it makes sense. And that depends though on the way classical uses the quantum side. Like in the Monte Carlo example that you mentioned, you pre-prepare everything, then you run it, and then you come back. But like if you have some sort of offload where the HPC is waiting for this, there could be some corner cases that need to be handled, right?
100%. And this is what you. I mean, that statement is. I really love that statement, because that shows that it's so when we talk about those type of optimizations, optimizing access to classical and quantum resources, then this is so dependent on the actual workload you have, right? It's very difficult to kind of make a general statement of what's the best architecture.